Good afternoon. My name is Peter O'Brien from VCE, Vienna Consulting Engineers. On behalf of our project team, I'm honoured to be named as finalist in the 2021 Building Smart International Awards Program, and I'm very proud to present our work here today. Our technology solution is a collaborative effort developed by the corporate startup STRUCINSPECT and VCE, Vienna Consulting Engineers. Both companies are based in Vienna, Austria. For this award submission, we have chosen to demonstrate our technology solution based on a project undertaken for the Autobahn GmbH, the Motorway Management Authority in Germany. The particular structure on which we have chosen to demonstrate our solution is an infrastructure bridge on the A99 motorway ring around Munich. So I'd like to begin by providing a high-level overview of what our technology actually does and what inspired us to develop this idea. But first things first, our technology addresses the field of digital asset management, and it facilitates the digital structural inspection and maintenance management of concrete structures. Our overarching ambition with this technology is to optimize, automate, and ultimately make a digital structural inspection more accessible for the mass market. In turn, we aim to promote the wide-scale industry adoption of an open BIM-based structural inspection standard. The central component in our technology solution is the STRUCINSPECT platform, which enables a civil engineer in charge of a structural inspection to manage the entire lifecycle process. The platform is powered by an artificial intelligence-assisted damage detection procedure. Using only pixel images of a structure, the technology can detect, analyze, and classify damages according to the respective level of severity, dimensions, type, and any other attributes required to describe the damage. As part of the advanced inspection services, the platform also offers the provision of a digital twin in the form of a point cloud, textured 3D mesh model using photogrammetry. All of this can be managed through the STRUCINSPECT platform throughout the entire lifecycle. And now, the provision of IFC and BCF capability enables infrastructure operators to interface the entire open BIM universe. And now I come to our process diagram in order to help explain all of the procedures in our technology solution and to describe the journey from pixel to Pset. I've divided the entire process into 6 sub-processes: input data, digital inspection processes, digital inspection output, BIM processes, BIM output, and federated BIM output. So, beginning with input data, the reason our project is titled Pixel to Pset is because, as an input, all we require to begin this process is really only a collection of high-resolution pixel images of a structure. Such images are often taken using drones for larger structures where we encounter difficult terrain or in order to reduce or eliminate disruption to road or rail operation, as well as to reduce the costs associated with scaffolding and setting up platforms on site. The use of drones also helps avoid any risks associated with abseiling or working at height. However, terrestrial camera images can also be used for smaller structures. Typically, a 42 megapixel camera with a telescopic lens provides us with sufficient resolution to identify damages and create a digital twin. For the A99 project, the terrestrial camera was used instead of drones on account of the small size of the structure. So, based only on this input data, we have 2 primary operations that are performed as part of the digital inspection. The first one is the creation of the digital twin. As part of the STRUCINSPECT advanced inspection services, a digital twin can be created using photogrammetry. The result of this process can be either a point cloud or a textured 3D mesh model, depending on the end user's requirement. However, either point cloud or textured model can be used equally as well, as we'll see later when we describe the BIM processes. For the A99 project, we actually also had a terrestrial laser scan to assist us. But in this case, it was only because the Autobahn GmbH required a much larger site to be scanned than just the bridge itself, and it was therefore quicker to scan such a large area with the laser scan. However, we also had the photogrammetric point cloud from the STRUCINSPECT Advanced Inspection Services, and this would have worked equally well for the purposes described in this process. And now we come to the core function of the STRUCINSPECT platform, and that's the artificial intelligence-assisted damage detection. This procedure processes the input images using neural networks with deep learning optimization to analyze discrete pixels in what is a highly sophisticated method that produces very detailed outputs. All defects are identified, analyzed, marked, documented, and classified according to the respective level of severity, dimensions, type, and any other attributes required to describe the damage. The procedure is trained to differentiate between many different damage types, the most common of which are cracks, spalling, and exposed reinforcement. One of the outputs of this process are segmented images showing the contours of the identified damages. In addition, all the damage data, such as type, size, classification, and severity, are recorded. So, two data sets are produced from the AI-assisted digital inspection. One contains numerous georeferenced 3D points, defining the contour polyline of the damage. And the other data set contains the damage attribute metadata. And here we see two examples. And this is all we need in order to produce our structural inspection BIM models. And now we finally come to the BIM processes. In order to interface with the BIM world, we use the Python IFC OpenShell to transform the two datasets into highly detailed, information-rich IFC4 structural inspection models and BCF 2.1 structural damages reports. Elements representing the damage's shapes, sizes, and positions are created as IFC extruded area solid geometry, as we determine through trial and error that such extrusions maximize visibility in the BIM model and provide the optimal graphical impact. The damage attribute data is then stored on a user-defined Pset. The tool currently exists as a headless back-end function without a graphical user interface, but we're currently in the process of preparing a front-end GUI to allow the end user to define their own attributes and export parameters. Nevertheless, even without a graphical front-end, the system is fully functioning, well-tested, and already fit for production. It's worth pointing out here too that the tool is more than just a straightforward IFC writer. It also undertakes several complex boundary curve optimization algorithms, numerical processes, and orthonormality checks required to prepare the raw data for BIM model generation. But unfortunately, I haven't got the time in 20 minutes to go into that level of detail. So instead, we'll jump ahead and have a look at the IFC output prepared by our technology solution. And here you can see that we've only produced extrusions floating around in space. This model is not particularly useful by itself, as one of the overarching goals of the technology is to be able to provide a clear graphical overview of the structural condition of the bridge, which means being able to show relationships between various damages and the context within which these damages have occurred. Therefore, we require a geometrical model of some kind to provide reference, orientation, and meaning to the structural damages model. So this raises the question then from where this reference geometry should come, and luckily there are a few options. Some clients or projects will require an information-rich as-built BIM model and others will not. In the case where an as-built BIM model is required, then a standard scan-to-BIM process can be undertaken in which the point cloud is used as a reference for the manual BIM modeling, using any off-the-shelf BIM modeling tools like Revit or ArchiCAD. Alternatively, the point cloud or textured 3D model itself can be used as a geometrical reference, and to great effect also. And I'll now show how both of these two alternatives can work. So for the A99 project, our client, the Autobahn GmbH, chose to invest in the complete as-built BIM model. The elements shown here in red are the bridge structure itself and the acoustic wall. However, the entire area around the bridge was also of interest and modelled accordingly. The resulting scan to BIM models was produced using Revit and handed over in 33 separate IFC aspect models. And to supplement this scan to BIM process, structural information from the original 1972 hand-drawn rebar drawings and subsequent inspection reports was entered manually into the BIM model. The resulting federated model then provides an orientation and a reference to our structural damages model. Here we can see clearly each damage as an extruded solid with exactly the correct location and size and all the relevant structural information, including links to images and structural inspection reports. This BIM model represents a self-contained single source of truth depicting the structural condition of a given structure at any given moment in time. Using our technology, all of this can be produced in an automated process based on simple pixel images. And the other alternative to an as-built BIM model is to use either the point cloud or the 3D texture model prepared by the STRUCINSPECT processes as a geometrical reference. For the purpose of visualizing and understanding the damages model, this approach works equally well and actually has the distinct advantage of avoiding the expense and effort of the manual scan-to-BIM production process. Now that we've covered the model production, we can go back and look at the other product from our IFC OpenShell operation. So, as a parallel process and based on exactly the same pixel input data, the BCF 2.1 damages catalog is created to accompany every IFC4 damages model. This report includes every damage identified at the time of the digital inspection, and using the BCF viewpoints, which are calculated numerically from the damage geometry coordinates, we can jump instantly to the respective damage. Thanks to the persistent and consistent GUID management system that we've implemented, we'll be able to track each damage throughout its entire lifecycle. This BCF damages report can then be uploaded into any BCF server. Here we've uploaded it into BIM Collab for demonstration purposes. We've implemented the BCF functionality in order to provide a mechanism by which information can be transported from the field directly back to the digital twin. This completes the digital round trip. This can be achieved using any tablet or head-mounted device. Here we see an example from the A99 of the HoloLens 2 in action. The device downloads the damage data directly from the STRUCINSPECT platform, and then, using BCF issues, the inspection engineer can monitor the evolution of each damage during the interim inspections. As a next step, server-hosted BCF collaboration is to be integrated directly into the STRUCINSPECT platform. But in the meantime, we can use any other BCF server, such as BIM Collab. And now we come to the last stop on the tour from Pixel to Pset, and that's the good old topic of 2D drawings. Put simply, 2D drawings are still required and will be required for some time yet. They're currently created manually or with considerable effort, whereas our technology solution enables efficient preparation of 2D drawings based on the IFC damages model superimposed over any geometrical model using an off-the-shelf BIM authoring software tool such as Revit or ArchiCAD. What's more, the geometrical model can be an as-built BIM model, a textured 3D model, or simply a point cloud. And to demonstrate this, I'll now hide the BIM model in this example here. And now we're looking only at the point cloud and our automatically generated IFC4 structural inspection model. And now, viewing the two side by side, we see that even without a complete as-built BIM model in the background, our technology enables the efficient production of a high-quality 2D overview drawing. Now I'd like to demonstrate a few of the immediate use cases of our technology. And the first main use case is to simply provide a better overview of the damages in any given structure, and more importantly, to help the civil engineer understand the relationships between damages in a structure. Being able to display the damages with such clarity enables a civil engineer to more easily identify a potential connection between two damages that may have otherwise appeared isolated or unrelated. In turn, this increases the chances that the correct mitigation measures can be identified, prescribed, and undertaken. The second immediate use case is to facilitate the BIM-based management and tracking of areas to be maintained. We have the ability using the STRUCINSPECT platform to draw areas manually on the images and enter any maintenance measures required for that particular damage. This sketch then gets automatically mapped onto the image surface, which in turn enables us to extract 3D coordinates and prepare an IFC and BCF model using exactly the same mention described earlier. These models can then be used to track and manage maintenance costs, measures, and forecasts using any third-party cost control software, like i2 for instance. And the third obvious and immediate use case is simply the ability for a civil engineer to complete the digital round trip using BCF. Current industry practice sees this information stored in minor inspection reports or addendums, whereas our technology solution improves the transparency and accessibility of this information by enabling an engineer on site to enter comments and damage updates directly into a tablet or augmented reality headset, and then transfer this information directly back to the BIM model via BCF server synchronization. So, to summarize what it is we've achieved with our technology, we've succeeded in combining several highly innovative technologies, which has culminated in a number of powerful use cases for OpenBIM. We've already attracted considerable interest from infrastructure operators here in Germany and Austria. Our solution offers the asset management industry a ready-to-use practical solution to an immediate challenge. In turn, this helps guide the asset management industry's digital transformation in the direction of open BIM standards. We've lowered the commercial and knowledge investment costs associated with the digital transformation by providing a self-contained and largely automated solution from pixel image through to complete BIM implementation. Our technology provides a civil engineer with a more complete overview of the structural condition of an object, as well as offering a method for the simplification of the creation of 2D drawings. Our technology provides all the ingredients required for a BIM-based cost calculation and management of maintenance surfaces across an entire infrastructure portfolio. And finally, via BCF, we've provided the site engineer the tools required to interact with the BIM model directly from the field, and thereby providing a mechanism for maintaining the BIM model in between periodic major inspections. And as a closing statement, we've invited the Autobahn GmbH to say a few words from the perspective of an end user.
Für uns sind offene Standards, also die sogenannte Open BIM-Methode, zwingende Voraussetzungen im Lebenszyklus der Bauwerke. Ganz einfach, weil wir nicht wissen, ob Softwareprodukte, die wir heute haben, in 10 Jahren noch am Markt sind und wie sich der Markt entwickeln wird und verändern wird. Also, die diesmal eingesetzte Technologie wird uns momentan nicht unmittelbar einen Mehrwert bringen. Das ist immer so, wenn man in neue Technologien investiert, aber wir sehen langfristig auf jeden Fall einen erheblichen Mehrwert. Und zwar sehen wir ihn dort in der Präzision der Schadensdokumentation und in der Nachvollziehbarkeit und der Transparenz der Schadensveränderung über die Zeit. Die Auswirkungen auf die Branche möchte ich zweigeteilt sehen. Einmal unmittelbar auf die Bauwerksprüfung. Sie wird die Bauwerksprüfung ein Stück weit verändern. Sie wird die Schadenserfassung und Dokumentation wesentlich vereinfachen. Damit wird sich die Tätigkeit des Bauwerksprüfers wandeln und dadurch auch vereinfachen, hoffen wir. Und die Branche insgesamt wird davon profitieren, dass wir die Digitalisierung insgesamt vorantreiben, und die Erfassung des Bauwerksbestandes und der Schäden ist der erste Schritt in dieser Richtung im Lebenszyklus eines Bauwerks. Für uns ist entscheidend die Dokumentation der Schäden über die Zeit und diese Nachvollziehbarkeit dieser Schäden, eines harmlosen Schadens, der heute eben ganz unbedeutend ist, aber plötzlich in 10 oder 20 Jahren eine ganz andere Dimension hat, und wir können dann den Schaden einwandfrei nachvollziehen, die Entstehungsgeschichte über den Lebenszyklus.
And of course, the project and the development of this technology was a joint effort involving the skills of many others, and in particular the vision and foresight of the client, the Autobahn GmbH. I'd like to take this opportunity to thank them all. And so once again, on behalf of the project team, I would like to thank Building Smart for providing us with this unique opportunity to showcase our application of Open BIM standards and solutions on the international stage. The awards process has challenged us to perceive and assess our own technological achievements through the eyes of others, and in turn has provided us with clarity and direction regarding the future development of our technology. We feel honoured to be selected as a finalist in the technology category, and we're grateful to Building Smart for their proactive campaigning for the Open BIM digital transformation.